I'm gonna start with chapter 7. Okay, so in chapter 7, this is when we're gonna do now. We're gonna do algebra. So okay, we have been doing algebra also. It's just that we were analyzing the trigonometric functions from the graphical point of view. We're looking at the geometric properties, if you want. Okay, we're looking at the graph, learning how to graph them, and then inverse functions and all of this business. Now we want to do more algebra. What I mean by this is we want to start solving equations that involve trigonometric functions. Okay, so to prepare ourselves for that, then we need to understand that there are a bunch of formulas and identities that can be used to be able to do this. Okay, and that's the first thing that we're going to do in this section. So in chapter 7, the main goal is to be able to solve trigonometric equations, but to do this you need to have some tools, and the first thing that you need is to know the basic identities. We already know them. I'm just going to remind you of this, okay, because they will be helpful as we solve some equations later on. So the way I'm going to do this is we're going to do some basic identities. I'm going to show you some examples how to use them, and then I'm going to go straight to 7.5, okay, and because we are already ready to do some simple trigonometric equations, so to start getting an idea of how to solve trigonometric equations. And then as they get more complicated, we will need some special formulas that trigonometric functions enjoy, and that's what's done in 7.2, 7.3, etc. So I'm gonna come back and we're gonna discuss those formulas, and then we're gonna use them as motivation to solve more complicated equations. Okay, but I basically want to center the discussion in this unit around solving trigonometric equations, because that's really what the upshot is. Anyways, this most likely will start happening next week anyways, but let us get these basic identities down. All right. Okay, so basic trigonometric identities, and then I'm saying here recall because we already have seen this. Okay, remember that we have there are certain groups like the so-called Pythagorean identities. These are, you know, sine square. Okay, let me use x. So sine square of x plus cosine square of x. What is this equal to? Who can tell me? Is equal to 1. Very good. And then remember that from here we can actually derive 2 more. Okay, from here we can actually easily see that if you do tangent square plus 1, this equals secant square, and also 1 plus cotangent square is going to be cosecant square. Okay, so these 3 guys, they are called the Pythagorean identities, and there is actually sometimes, usually they are not used this way, but they are used in a different form. In particular, the sine square plus cosine square equals 1. The one helpful way of using this is the fact that sine square then is 1 minus cosine square, right? So it's a way of writing sine in terms of cosine, and similarly cosine square you can write it in terms of sine as 1 minus sine square. And following the same ideas then on the others, this is how you write secant in terms of tangent, but then you can also write tangent. So tangent square is secant square minus 1. You're going to be using this a lot in calculus 2. This identity is going to be popping up left and right. And then cotangent square is cosecant square minus 1. So these are the Pythagorean identities. Then we have the even odd identities that we discussed them when we define the functions, right? So remember, all the trigonometric functions are odd with the exception of cosine and secant, which are even, okay? So sine of negative x, cosine of negative x, and tangent of negative x. Once you know these 3, then the other 3, they behave the same, right? Because they're just 1 over this. Those are the reciprocal identities. So the sine is an odd function, so the minus survive. Cosine is even, so the minus is gone. And tangent is odd, so the minus survive. Then because of this, then we get for free what happens to cosecant, secant, and cotangent. The cosecant is odd. the secant is even, and the cotangent is odd. The reason for that is the next set, which are actually the reciprocal identities, right? Which are, again, it looks like a lot, but you already have this knowledge. You already know all of these, okay? Just summarizing what you know. Reciprocal identities, remember, these are the definition of cosecant, secant, cotangent. So cosecant of x, we define this as 1 over sine. The secant of x, remember this was 1 over cosine, and cotangent of x, this was 1 over tangent. But therefore, if you have this, then you also have the fact that sine is 1 over cosecant, cosine is 1 over secant, and tangent is 1 over cotangent. All right, those are the reciprocal identities, and then we have the quotient identities, which are, the fact that tangent is sine over cosine. You're going to use this a lot in calculus 1, calculus 2. It's going to be popping left and right. And also because, cotangent is 1 over tangent, that means that if you flip this, then you get the cotangent is cosine over sine. So all of this collectively is what I refer to as the basic identities, okay? Are there any questions on any of this? I mean, we have talked about this already before, but do you have any questions, any concerns on this? Okay, so like I said, even though it may look like a lot, you should know this, okay? So at this point, I think you should already know all of these identities. Maybe you may not remember these ones here, but then just make sure that you do, because those are important, okay? But the others are kind of the definition. They follow by definition, basically, okay? All right, so now let's go ahead and let's put this to use. So let's do some examples. How is it that we're gonna use this? So we use this to actually, verify identities. So what's an identity? An identity is an equation that's always true, okay? So let's see, let me show you this. So verified identity, in other words, to make sure that what we have is really an identity. So verified identity, and then first, let's do tangent of theta times cosine of theta equals sine of theta. Okay, so this one is a very easy example, okay? But it actually illustrates the purpose of this. So again, to verify an identity is to show that this expression, this expression that I wrote here is always true. This equation is always true. In other words, no matter what theta is, the left-hand side is always equal to the right-hand side. So this is the left-hand side equals to the right-hand side. So to verify this identity, all you have to do is begin with one of the sides and then show that that is always equal to the other one. As a general rule, you should always begin with the more complicated side, because that will give you something to work with, okay? If you begin with sine, then you have to be more creative to go from the right to the left in this particular example, okay? But the left-hand side looks more complicated, so it's easy to solve, to start with that. So I'm going to begin with the left-hand side, which is tangent of theta times cosine, and our job is to show that this equals the right-hand side. Well, let's see. And you will do that by using one of the identities, okay? So for example, we can use the fact that tangent is sine over cosine. So this is the same thing as sine over cosine times cosine. And now, it becomes pretty simple. We see that the cosines cancel out. So indeed, we get sine of theta, which is the right-hand side. So we're good. No matter what theta is, it's true that if you do tangent times cosine, you will always get sine. Do you understand this? All right, so let's see. Let's put a couple here. So let's verify cosecant times cosine times tangent. That this is always equal to 1, regardless of the angle. And then let's do here CC 1 plus sine of x 1 plus sine of negative x, that this is always cosine square. And then let's have here d, let's do secant square of x minus 1 over secant square, but this is always sine square. Okay. All right, let's see. Let's do this. So for B, we have cosecant times cosine times tangent. We need to show that's equal to 1. Again, you can start with either side and show that it's equal to the other one. But again, if you start with the right-hand side here, which is 1, I mean, what do you do after that? And so, you know, then you need to start getting more and more creative, and that makes it very difficult. So it's easier to begin with the most complicated side, the one that looks like has a lot of stuff going on, okay? And then you start using identities to hopefully start, you know, getting towards the right-hand side. So I'm gonna begin with the left-hand side, which is cosecant times cosine times tangent. And then I'm gonna start using identities. So let's see, what do we know about cosecant? Cosecant is the same thing as 1 over sine, right? I'm gonna leave cosine as it is. And then tangent is the same thing as sine over cosine. And you know, now again, it becomes pretty simple. What happens? We see that the sines cancel out, the cosines cancel out, so we are left with 1, which is indeed the right-hand side. So again, very good. Questions? Okay. All right. So yeah. So let's see. Try C. Why don't you try C on your own? And I'll give you 3 minutes, because you're just playing with the equations to make sure that they equal each other. So you use the identities, and then you need to, you know, have the identities present so you can make the correct decision. All right, so I give you 3 minutes, try C, and then if you do it quick, then try D. Then we do it together. Okay, so let's give it 1 more minute. Okay, let's see. So again, you know, here is you actually need to convince yourself you did it correctly or not, because you know, just use algebra and identities, and then the idea, you know, that you did it correctly if you started with the left hand side and you successfully reach the right hand side, okay, without forcing anything to happen. So let's see. You need to decide first, how do you begin? Should we begin with the left or with the right in this particular case for C? Which one should we begin? The left, right? So that one is the one that looks more complicated. So let's do it. So left hand side. So this would be 1 plus sine times 1 plus sine of negative x. So the question usually, it kind of starts telling you what to do, right? For example, if you see this, hopefully the first thing that comes to mind is, okay, let's use the even odd identity. So there's a sine of negative x, then, you know, we can write this as 1 plus sine. I don't touch the first one. Then the other one is the same thing as 1 minus sine. Everybody okay with this? Okay, so now the next thing, well, let's go ahead and let's multiply this, but you see that this is a difference of squares, right? Because these are a product of conjugates, so this would be equal to 1 minus sine squared. And you multiply, and you clear the parentheses. And if you see 1 minus sine squared, then it should come to mind immediately the Pythagorean identity, which is the same thing as cosine squared. And this is the right hand side, so we're good. Questions? All right, so let's see, let's take a look at D. And in D, I'm going to show you that actually, you know, there are different ways that you can do this. The last part. So what last part you mean? From the second line to the third line? Okay, that's one of the identities. Remember, what do you know about sine squared plus cosine squared? So what's sine squared plus cosine squared? That's equal to 1. So what's 1 minus sine squared then? So if you move the sine squared to the other side, what do we get? We get the 1 minus sine squared becomes cosine squared. Do you understand this, Emily? All right, so that's what's going on. Okay, so let's take a look at D. And in fact, D, I'm going to show you that we can actually do D in 3 different ways. And there could be other ways, okay? So the point that I want to make is that you may take one approach and then somebody else may take another approach, and it doesn't mean that one of you is wrong, okay? So as long as you do everything correctly algebraically, then you're both correct. So for example, this one, let's do it in 3 different ways. And maybe what I decide to do as my way number 1 is probably not what you think about initially, or maybe you did, okay? So, but we're gonna do it in different ways. Anyways, let's see. I'm gonna do one that I believe is the fastest one, okay? So, option 1, let's see, option 1. Again, the left-hand side is the most complicated, so I'm gonna begin with the left-hand side, right? And one thing that we could do here is the following. So this one is actually pretty fast. We can split this as 2 fractions. So you can split this as secant squared over secant squared minus 1 over secant squared. So then the secant squares cancel out, of course. So we're going to get 1 minus. Now remember, 1 over secant is cosine. So this is just 1 minus cosine squared. And then what is 1 minus cosine squared? This is sine squared of x, right? Which is our right hand side. So we're good. We started with the left and we end up with the right. You okay with this? All All right, so but let me show you a couple more options. For example, option number 2, another alternative would have been the following. Let's use the identities that we have here. For example, you know that tangent squared plus 1 is equal to secant squared. That's one of the Pythagorean identities. So secant squared minus 1 is tangent. So we can write this as tangent squared over secant squared. So now what's tangent? Tangent is sine over cosine. So this would be sine squared over cosine squared. And then secant is 1 over cosine. So this would be 1 over cosine squared. And remember, when you divide fractions, you multiply and you have to flip the second fraction. So really what's going to happen is that the cosine square here will cancel with this cosine square. So this is going to leave you with sine squared, which again, you okay with this? All right. And let's see, let's throw in an option number 3. So option 3 can begin with the left. And then one thing that you can do is, okay, let's write everything in terms of sine and cosine. In this case, it would just be cosine, because here, so, and this is something that you should take with you when you go to calculus, okay? Whenever you see trigonometric functions and you have no idea what to do, here is something that you can. Look, tangent is always sine over cosine. Cotangent is cosine over sine. And secant and cosecant, they are 1 over sine, 1 over cosine, and 1 over sine respectively. So the moral of the story is these 4 trigonometric functions, tangent, cotangent, secant, cosecant, you can always write it using sines and cosine. So when you have no idea what to do, just write everything in terms of sine and cosines, and then hopefully something will pop up that you can do, okay? And if you do this, you will get out of some tight spots in many situations. All right, this will be very relevant in calculus too. Okay, anyway, so here let's do that. I'm just gonna write everything in terms of cosine this time. So secant squared is the same thing as 1 over cosine squared, and here 1 over cosine squared. And for example, we can just clear this little fraction. So I'm gonna multiply top and bottom by cosine squared. Let's multiply top and bottom by cosine squared of x. So this then becomes 1 minus cosine squared on top over 1 in the bottom. And then as you know, 1 minus cosine squared, that is sine squared. So this one is essentially very similar to option number 1, if you think about it, okay? But instead of splitting as a fraction, we first went directly to cosine, and then we cleared denominators, and then everything became pretty easy after that. Okay, questions? All right, so let's do one more. Let's put here number 2. How about, actually, let's see, we call it D, let's call it E, because we're still verifying stuff. So E, how about this one? Sine squared of negative theta minus cosine squared of negative theta divided by sine of negative theta minus cosine of negative theta. So let's show that this is just cosine of theta minus sine of theta. So verify this. Okay, so just by looking at this, you should realize that we begin with the left-hand side. Then we first are going to use a bunch of the even odd identities, and then we see what to do from there, okay? So let's see, left-hand side is sine squared of negative theta minus cosine squared over sine of negative theta minus cosine of negative theta. All right, so let's get rid of all of those negative theta. And the reason why we're doing that is because on the right-hand side, there is no negative theta, okay? So let's get rid of those. So first of all, the sign is odd, so the minus comes out, but because we have sine squared, the minus is actually gone, right? So that's just sine squared of theta. Cosine, the cosine makes the minus go away, so that just becomes cosine squared of theta. Now in the denominator, we do have some minus surviving. The minus inside the sine comes out, and then the minus inside the cosine disappears because it's an even function. So we get these using the even odd identities. So next, when we look at the top, we see there's a difference of squares, so we can factor, right? So it becomes sine plus cosine times sine minus cosine. And then in the bottom, notice that we can factor out a negative. So it becomes sine plus cosine. And now it's kind of clear what to do. This parenthesis cancel with this one. And so we are left with sine minus cosine divided by -1. But if we distribute that -1 over, then that flips the top, right? So then this becomes cosine minus sine, which was our right-hand side. So we're good. Okay, questions on this example? Any questions on this? All right, sounds good.